Good evening, friends. Now we wish to hear about Big Bang. We wish to hear about Big Bang. Now, this is a picture of Big Bang, the process of the formation of this universe that is composed of galaxies, planets, stars, etc. This picture is showing the time period of different phases of synthesis of this universe from the mm, elementary particles to atoms, atomic nucleus, then stars, galaxies, etc. The inflation of this universe. This picture is showing how from singularity and Big Bang, the galaxies, planets, stars are formed, the expansion and retraction of this universe, which is known as the Big Bang cycle or the Big Crunch theory works. The Big Bang event is a physical theory that describes how the universe expanded from an initial high density and temperature. Various cosmological models of the Big Bang explains the evolution of the observable universe from the earliest known periods to the subsequent large-scale form. Detailed measurements of the expansion rate of the universe place the Big Bang singularity at an estimated 13.787 plus minus 0.020 billion years ago, which is considered the age of the universe. Singularity. Extrapolation of the expansion of the universe backwards in time using general relativity yields an infinite density and temperature at a finite time in the past. This irregular behavior, known as the gravitational singularity, indicates that general relativity is not an adequate description of the laws of the physics in this regime. Models based on general relativity alone cannot fully extrapolate towards the singularity. The time that has passed since that event, known as the age of the universe, is 13.8 billion years. Despite being extremely dense at this time, far denser than is usually required to form a black hole, the universe did not recollapse into a singularity. Commonly used calculations and limits for explaining gravitational collapse are usually based upon objects of the relativity constant side, such as stars, and do not apply to rapidly expanding space such as the Big Bang. Since the early universe did not immediately collapse into a multitude of black holes, matter at that time must have been very evenly distributed with a negligible density gradient. Inflation and baryogenesis. The earliest phases of the Big Bang are subject to much speculation since astronomical data about them are not available. In the most common models, the universe was filled homogeneously and isotropically with a very high energy density and huge temperature and pressures, and was very rapidly expanding and cooling. The period up to 10 to the power minus 43 seconds into the expansion, the Planck epoch, was a phase in which the four fundamental forces, the electromagnetic force, the strong nuclear force, the weak nuclear force, and the gravitational force were unified as one. In this stage, the characteristic scale length of the universe was the Planck length, 1.6 into 10 to the power minus 35 meter, and consequently had a temperature of approximately 10 to the power 32 degrees Celsius. The Planck epoch was succeeded by the Grand Unification epoch beginning at 10 to the power minus 43 seconds, where gravitation separated from the other forces as the universe's temperature fell. At approximately 10 to the power minus 37 seconds into the expansion, a phase transition caused a cosmic inflation during which the universe grew exponentially, unconstrained by the light speed invariance, and temperatures dropped by a factor of 1 lakh. At a time around 10 to the power minus 36 seconds, the electroic epoch begins when the strong nuclear force separates from the other forces with only the electromagnetic force and weak nuclear force remaining unified. Inflation stopped locally at around the 10 to the power minus 33 to 10 to the power minus 32 seconds mark, with the observable universe volume having increased by a factor of at least 10 to the power 78. Reheating occurred until the universe obtained the temperatures required for the production of a quark gluon plasma as well as other elementary particles. Temperatures were so high that the random motions of particles at relativistic speeds and particle-antiparticle pairs of all kinds are being continuously created and destroyed in collisions at some point at an unknown reaction called baryogenesis violated the conservation of baryon number, leading to a very small excess of quarks and leptons over antiquarks and anti-leptons of the order of 1 part in 30 million. This resulted in the predominance of matter over antimatter in the present universe. Cooling, Big Bang nucleosynthesis and cosmic microwave background. Panoramic view of the entire near-infrared sky reveals the distribution of galaxies beyond the Milky Way. Galaxies are color-coded by redshift. The universe continued to decrease in density and fall in temperature. Hence, the typical energy of each particle was decreasing. Symmetry breaking phase transitions put the fundamental forces of physics and the parameters of elementary particles into their present form, with the electromagnetic force and weak nuclear force separating at about 10 to the power minus 12 seconds. After about 10 to the power minus 11 seconds, the picture becomes less speculative, since particle energies drop to values that can be attained in particle accelerators. At about 10 to the power minus 6 seconds, quarks and gluons combine to form baryons such as protons and neutrons. The small excess of quarks over antiquarks led to a small excess of baryons over antibaryons. The temperature was no longer high enough to create either new protons and new proton antiproton or neutron antineutron pairs. A mass annihilation immediately followed, leaving just one in 10 to the power 8 of the original matter particles and none of their antiparticles. A similar process happened at about 1 second for electrons and positrons. After these annihilations, the remaining protons, neutrons, and electrons are no longer moving relativistically, and the energy density of the universe was dominated by photons with a minor contribution from neutrinos. A few minutes into the expansion, when the temperature was about a billion Kelvin and the density of matter in the universe was comparable to the current density of Earth's atmosphere, neutrons combined with protons to form the universe's deuterium and helium nuclei in a process called Big Bang nucleosynthesis (BBN). Most protons remained uncombined as hydrogen nuclei. As the universe cooled, the rest energy density of matter came to gravitationally dominate that of the photon radiation. After about 3,79,000 years, the electrons and nuclei combined into atoms, mostly hydrogen, which were able to emit radiation. This relic radiation, which continued through space largely unimpeded, is known as the cosmic microwave background and structure formation. Over a long period of time, the slightly denser regions of the uniformly distributed matter gravitationally attracted nearby matter and thus grew even denser, forming gas clouds, stars, galaxies, and the other astronomical structures observable today. So, this is the process of expansion of this universe and formation of this universe, galaxies, and etc.